Thank you. Hello, I'm Zoltán Kolarowski. I'm a PhD student from Eötvös Loránd University, and I'm also a junior research fellow from Wigner Research Center for Physics. And today, I will talk about generalized group designs, overcoming the four-design barrier, and constructing novel two designs in arbitrary dimensions. But first, let me introduce you to my team. The person on the left is the first author, Ágoston Kaposi, and on the right is Adrián Solymos. They are fellow PhD students. And the last person on the slide is our supervisor, Zoltán Zimborás. I am very grateful to have the opportunity to work with them. First, let's recap the definition of a unitary T-design. A unitary T-design is a finite subset of the unitary group which may replace sampling from the full Haar measure, as stated before. So you have on the left-hand side a finite summation over the design, and on the right-hand side you have the full Haar measure integration. And you can equivalently state it for that all M operators, you have this so-called twirling over the finite set should be equal to the twirling over the full unitary group with the Haar measure. And there are many applications to unitary designs in quantum information science. For example, quantum cryptography, quantum data hiding, channel fidelity estimation, quantum process tomography. These use one or two designs. State distinction uses 4 designs, and shadow tomography and thrifty shadow tomography uses 3 and 4 designs respectively. So the most prominent example, the most nice example of unitary T-designs are those which also admit a group structure, so-called group T-designs, or another name, T-groups. And for example, any irreducible unitary representation of a finite group constitutes one design. The Clifford group in prime power dimensions constitute a 2 design, and the multipartite Clifford group in 2 power dimensions constitutes a 3 design. But there is an obstruction to constructing group designs. So there is a result from the classification of group designs that for dimension larger than 2, there are no group 4 designs. However, for thrifty shadow tomography, you need an exact 4 design for it to be maximally effective. And surprisingly, the Clifford group gives a maximally ineffective scheme. So motivated by all these examples, our goal is, we have set out 2 goals. The first goal is that we need to construct exact unitary 4 designs in higher dimensions than 2. And we need to construct exact unitary 2 designs in arbitrary dimensions. And our main objective is, or the main tool is, find unitary designs using finite group representations. So for that, I will revise some basics and notations. So let's recap the representation theory of the unitary group. So tensor products of the vector space V decompose under the action of the unitary group into irreducible subspaces. And these irreducible subspaces are labeled by Young diagrams. For example, you have here the 4-fold tensor product of the defining representation of the unitary group, which decomposes into 5 parts labeled by 5 different Young diagrams with different multiplicities given by the Littlewood-Richardson rule. And if we evaluate, using this knowledge, the integral in the definition of the design, we will get an operator on the right-hand side here. And that means that we can rewrite our condition for being a unitary T-design to have this finite sum to be equal to this operator here. And the idea is that we have to search for finite subgroups in the unitary group which have such representations. For example, let's have T equal to T. So let's have a subgroup G of the unitary group with defining representation pi. And let's have the 2-fold tensor product of this. The 2-fold tensor product decomposes into a symmetric part and an anti-symmetric part. And the obstruction here is that these representation, when restricted to the finite subgroup G, may branch into smaller irreducibles when restricting to G. But when both of them are irreducible, stay irreducible, on the symmetric and anti-symmetric subspaces. For example, if you use the Clifford group in prime power dimensions, then you will get this expression. And this expression means that you essentially have a unitary group 2 design because it fulfills the relation which you have prescribed. So the idea is that we can search for finite subgroups that stay irreducible on the unitary group irreducible subspaces for larger T's as well. But there is an obstruction to that, which we have discussed, that you couldn't have a unitary group for design in large enough dimensions. So we need to overcome this barrier. So the question is, what if you have a subgroup which is irreducible or stays irreducible on the symmetric subspace and another one which stays irreducible on the anti-symmetric subspace? Can we get a 2 design using these? And the answer is yes. We have to twirl first with H and then with K, which will yield this operator which we need to achieve. And if we twirl first with H and twirl second with K, the consecutive twirlings will be equivalent to a single twirling by forming these pairwise products of the groups. So K.H forms a 2 design. This is an illustration of the idea. So if we twirl first with the subgroup H, we know that that stays irreducible on the symmetric subspace, then we will get a scalar times an identity in this sector. And in the other sector, we may get, for example, another irreducible with multiplicity 1, another irreducible with multiplicity 2, and this is part of the anti-symmetric subspace. So, but it decomposes. And if we twirl with K as well, K will be irreducible on the anti-symmetric subspace, so we will get this operator here, which we needed. So that constitutes a unitary 2 design. So for example, we can construct a 2 design in dimension 6. For example, if you use the projective special unitary group over a certain field, that has it has a representation irreducible on the symmetric subspace, and the alternating group of order 7 has a representation irreducible on the anti-symmetric subspace. It is called a standard representation. By forming the product of these 2 groups, the pairwise product of these 2 groups, it constitutes a 2 design. And the question is, can we find higher order T design using the same method? And the answer is yes, by using the same idea. So if we have multiple finite subgroups of the unitary group, and we multiply them together, as I described before, we get a generalized group T design if it forms a unitary T design. So that's essentially a definition. And the concept of a generalized group design essentially captures the idea of consecutive twirling with these subgroups. And there is a theorem related to generalized group T designs, which is that it forms, so this product forms a generalized group T design if for each Young diagram gamma, there is a subgroup for which the restriction to this subgroup of pi gamma is irreducible. Moreover, this representation should not appear elsewhere in the decomposition. And we need to search for representations of finite group with these appropriate irreducible restrictions. And we have found several examples. 2 of them is here. For example, we have found for design in dimension 6. So we have 2 groups which stay irreducible on 4 subspaces, and we have another group which stays irreducible on the remaining 1 subspace. And we have found a 4 design as well in dimension 12. We use the 6-fold covering of the Suzuki group, which stays invariant on 4 subspaces, or irreducible, sorry. And the standard representation of the alternating group of order 13 will stay irreducible on this subspace. And we have used the GAP computer algebra system for that, and we harvested character tables to find these examples. So yeah, now that we have solved or partially solved the this finding of 4 designs using finite group representation theory, we may be able to apply the same idea or similar ideas to forming or constructing 2 designs in arbitrary dimensions. And for that, we need a lemma. So this lemma says is that if you have an orthogonal 2 design, an orthogonal 2 design is almost the same as a unitary 2 design, but you need to exchange the unitary group into the orthogonal group in the definition. So if you have an orthogonal 2 design, then you can automatically get a unitary 2 design by forming this product. So by choosing a correct unitary matrix or unitary operator, and by conjugating the orthogonal 2 design using this and forming this product, we can get a unitary 2 design. This is an illustration of the idea that we need to find a sweet spot of this V alpha unitary matrix, and if we find a proper alpha star here, then we may be able to transform the coefficients, as we will see, in order to make it a unitary 2 design. So we how we do this? This is a proof sketch. So the abstraction is that the restriction of the symmetric subspace, when we restrict to the orthogonal group, it will decompose into a trivial representation and a rest representation. We call it rest. And these are irreducible. And therefore, the finite sum will decompose into 3 parts. And we know that if the coefficient for the trivial representation and the coefficient for the rest representation would be the same for all M operators, then it would constitute a unitary 2 design. So the idea is to try another twirling. And the statement is that if we twirl with this W alpha, and if we choose correctly this alpha parameter, then we can transform this into an operator where the coefficients are the same. So we will get a unitary 2 design. So the idea here is very similar as before, that if you twirl first with the orthogonal 2 design, as I have mentioned before, that you have 3 components. You will have this trivial component and this rest component here. These are irreducibles. And you need the coefficients of these components to be equal. But if we twirl again with this set where we conjugated with this W, with correctly chosen W unitary, we will get a unitary 2 design because the coefficients will be equal in this sector. And we will use this lemma for the alternating group. So we use the standard representation of the alternating group, which comes from the natural representation. And the twofold tensor product of the standard representation of the alternating group, when D is larger than or equal to 5, decomposes into 4 parts. But the antisymmetric space is antisymmetric subspace is good for us because it stays irreducible, but we need the other ones to make their coefficients to be equal. And the idea is that the standard representation here and the rest representation, which are irreducible again, if they would not decompose, then we would get an orthogonal 2 design, because it looks as the orthogonal 2 design, which I have shown before. And the idea is that we need to, again, transform the coefficients accordingly. So the statement is that we can do that. We can find this orthogonal transformation, which leaves the trivial and the antisymmetric subspace irreducible, invariant, and by conjugating this set with this, then we will get an orthogonal 2 design. And then, if we have an orthogonal 2 design, then we automatically get a unitary 2 design. So the proof goes as follows, that we do the first twirling, then we get, with the standard representation of the alternating group here. So we know that we will get 4 components here. And similarly as before, we need to find an orthogonal transformation such that this V conjugated by O times V forms an orthogonal 2 design by achieving that the coefficients will be equal. And yes, and the statement is that we have found this, but I won't go into detail here. So the idea is, again, very similar to the previous ideas, that you have this symmetric subspace, and there you have the standard and the rest representations here with potentially different coefficients. But in order for the coefficients to be equal for all M operators, we can twirl with another copy of this orthogonal, or this, not orthogonal, the standard representation of the alternating group conjugated by a proper orthogonal matrix. We will have the coefficients be the same, and then we get an orthogonal 2 design. And by using the previous lemma, we get automatically a unitary 2 design. So this is essentially another illustration of doing that. This is very similar to the one we had before for the orthogonal 2 design, that what we did is that we have found an orthogonal transformation which over-transforms the coefficients. And we know that everything is continuous. So by over-transforming it, we know that we can find a sweet spot. And we did find a sweet spot where we get an orthogonal transformation. And by conjugating the original set of the standard representation of the alternating group, then we can form an orthogonal 2 design, which is here. And by another transformation or another unitary transformation here, we can get to a unitary 2 design as well. And therefore, we have constructed a unitary 2 design in dimensions larger than or equal to 5. So, conclusion. The present work provides a method for constructing T designs from certain well-behaving groups, with several examples, which I have shown before. And we have provided an explicit construction of a 2 design in dimensions larger than or equal to 5. And all these ideas rely on finding groups which branch irreducibly in the unitary group on these invariant subspaces. And finding these may yield more results. For example, if we find more of these, we may be able to find higher order T designs for T equals to 4 or 5. And we may be able to find explicit construction for 3 designs in arbitrary dimensions as well. And there are also further directions. For example, we may be able to generalize this idea to the concept of approximate designs, and we may be able to use these constructions in applications. For example, the 4 design construction in thrifty shadow tomography. Thank you for your attention.
Are there any questions?
Yeah, thanks for your amazing results. So can we see just very simple question? So can we see some improvements in terms of gate resource or efficiency over the just randomly stacking the neighboring random unitary gates to achieve some approximate T design?
So are you asking about the depth of the design, or what do you refer?
So because I think this result seems to show some groups unitary T design in the low dimension, but actually we can achieve some approximate T design by just randomly stacking stacking just randomly random unitary neighboring gates with a sufficient depth. So maybe have you thought about some gate improvements of your theory over this just previous methods?
We haven't talked about it. We didn't think about it, I think.
Okay, yeah. Thanks. Yeah.
What's the cardinality of the 2 designs that you constructed?
Oh, it's very large, actually. So we use the alternating group with several copies. So it's
very big.
So it's quite big. So if we calculate it, then it would be n to the n factorial over 2, and we use like 4 copies, so to the power of 4, so it's pretty large actually.
So in these non-prime power dimensions, there's some huge gap between the best known exact 2 designs,
There is,
and
but
it's kind of interesting. It's such a big gap.
yeah, but it's an explicit, yeah, but
I agree. I'm just saying it's kind of interesting that your construction requires such a large cardinality, and in the other dimensions, it's pretty low, like d squared or something. Yeah. Thank you.
Does your construction also automatically give a circuit for preparing these unitaries?
No, we didn't think about circuits, so we didn't look at the depth of these constructions. Not yet, but we will.
Okay, looking forward to that for next QP. Any other questions? Okay, if there are no more questions, let's thank speaker again.